Good afternoon, welcome. I'm Neha and today we are going to be talking about P block elements. So this is my first class with you. P block elements is a topic of a lot of deliberation because first it was deleted from NCERT and then it came back into Neet syllabus. So you need to know that the P block elements is a part of class 11th as well as class 12. Alright, class 11th has group 13 and group 14, class 12th has the remaining groups. Let us see what P block elements are. This is the periodic table. The elements on this side of the periodic table, these ones here, are the P block elements. So what happens in P block elements, the valence electrons, they enter the P shell. And hence, since in a P shell there are 3 subshells in which 6 electrons can come in all, it means that there are 6 P block groups. So this is the first group, that is the group 13, starts with boron, aluminium, gallium, indium, thallium and nihonium and so on. Next is group 14, 15, 16, 17 and 18. Group 18 is noble gases, starts from helium and goes till this one, last here. Now let's see what are some salient features of P block elements. Now in P block elements, these lines are from your NCERT, okay, so that you relate to them more. In P block elements, the last electron enters the outermost p orbital. The maximum number of electrons that can be accommodated in a set of p orbitals is 6. Consequently, there are 6 groups from 13 to 18. Alright, now let's talk about their valence shell configuration. P block elements, if we talk about their electronic configuration, in the valence shell, starts from group 13, 14, 15, 16, 17 and 18. NS2 NP126 is the general electronic configuration for the valence shell here. Alright. Good afternoon, Ishka, Shruti, Nontu, good afternoon. Right. So NS2 NP126. For group 13, the outermost or the valence electronic configuration would be NS2 NP1. For 14, NS2 NP2. For 15, NS2 NP3. For 16, NS2 NP4. 17, NS2 NP5. And for 18, which are the noble gases, NS2, NP6. So these are the valence shell electronic configuration. They are followed before these valence electrons. Obviously, there is a full core of electrons. Right. Now, the maximum oxidation state shown by a P block element is equal to the total number of valence electrons. So this is called the group oxidation state. What is the group oxidation state of P block elements? 1, it means that it is the most common oxidation state exhibited by that group. How is it calculated? You add up the number of S and P electrons. So for group 13, the group oxidation state will be +3. For group 14, add up the 2 electrons here. So it will be +4. For 15, it will be +5. For 16, +6. For group 17, +7 and this is +8. So the most common oxidation state would be 3, 4, 5, 6, 7 and 8. This is called the group oxidation state. Now there is another very interesting phenomena. I'll just tell about it in brief, but we'll go more in detail when we talk about group 13 further down the class. So it's called the inert pair effect. What happens in the inert pair effect? The stability of this group oxidation state decreases as you move down the group. So if we see in the periodic table, in group 13, the stability of the +3 oxidation state on moving down the group to thallium decreases. The reason behind this will be discussed when we talk about the inert pair effect, but this means that the oxidation state which is 2 less than the group oxidation state, that means +1 here, becomes more stable as you move down to thallium. This is called the inert pair effect. Apart from the group oxidation state, many other oxidation states are also exhibited. We will talk about them when we talk about their respective groups. Moving on. The elements may show other oxidation states which differ from the total number of valence electrons by unit of 2. This is called the inert pair effect. In boron, carbon and nitrogen families, the group oxidation state is the most stable state for the lighter elements in the group. If you talk about group 13, 14 and 15, the group oxidation state of +3, +4, +5 is the most stable for the lighter elements. Now, the occurrence of oxidation state 2 less than the group oxidation is attributed to the inert pair effect. Now, another very interesting thing about p block elements is that this is the only block where non-metals and metalloids exist. Metalloids are elements whose properties lie between those of metals and non-metals. So, p block is the only block where non-metals and metalloids exist. So, if you see this here, boron here, carbon, silicon, nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, tellurium, fluorine, chlorine, bromine, iodine, and all of these are all non-metals, and then these are metalloids, and as you go down the group, the metallic character increases. So, these elements are all metals here. One more thing you will notice that at the end of the p block elements, there are some elements here: nihonium, flavorium, moscovium, livermonium, tennessine and ogasin. All these are synthetic elements. So, their half-life, they are man-made, they are radioactive, and their half-life is, it varies from a few seconds to a few nanoseconds also sometimes. So, their chemistry is not really studied. So, we will not be talking about these when we talk about the p block elements, and we limit our discussion till here. Alright. Now, let us see what type of bonding exists in p block elements. So, now that there are metals, non-metals and metalloids present, what happens? Now, there are three types of bonds. How does bonding occur? So, if you have two elements which are supposed to bond with each other, what will they do? They will try to achieve the most stable electronic configuration. To do that, they will either gain electrons or lose electrons, or they will share electrons. And the most stable electronic configuration you all know is of noble gases. So, they will try to achieve the configuration of the nearest noble gas. In doing so, you will see that if there are two electronegative elements, and if there is a bond between two electronegative elements, it will always be a covalent bond, like in the case of Cl2 molecule. So, chlorine is electronegative, it is a non-metal, it does not want to give its electrons, it only wants to gain electrons. So, what will happen in such a case? Both the chlorine atoms will, one electron from each chlorine atom will be shared between the two, and hence both of them will achieve their noble gas configuration. Such a bond where sharing takes place is covalent bond. So, if we have one electronegative and one electropositive element, this will give us an ionic bond. What happens in an ionic bond? In an ionic bond, one atom gains an electron, the other one loses an electron. For example, in the case of NaCl, sodium is a metal, it is electropositive, chlorine is a non-metal, it is electronegative. Sodium will try to lose one electron to achieve the noble gas configuration of helium, that is the nearest noble gas, and chlorine would want to gain one electron. So, this is an ionic bond. If there are two electropositive elements, two electropositive elements form metallic bonds. So, in metallic bonds, the valence electrons are not really bonded, they are free to move around, but we will not be talking about this in our current discussion. So, we will be focusing on covalent bonds and ionic bonds. Another interesting type of covalent bond is called a dative bond. dative bond or a coordinate bond. So what exactly is a dative bond? A dative bond is a type of a covalent bond only, but in this case, let's say we have two elements A and B. The pair of electrons that is shared between the two comes exclusively from one element, like this. Okay, once a dative bond is formed, it is not different from a covalent bond. It only differs in the way in which it was formed. Once it is formed, it is exactly like a covalent bond. So this is a dative bond. We'll be discussing a very interesting case of dative bond in the case of BF3 further down the discussion. All right. Moving on to general discussions about p block elements. Right. So we have talked about metals and non-metals. Non-metals have higher ionization enthalpies, higher electronegativities. They readily form anions, and the compounds formed by highly reactive non-metals with highly reactive metals are generally ionic, right? Compounds formed between non-metals themselves are largely covalent in character because of small differences in the electronegativities. This is also very interesting, this point here. It will come up again and again in the discussion of p block elements. You need to remember that the non-metal oxides are acidic or neutral, whereas the metal oxides are basic in nature. Right. Now, a very interesting property of p block elements is that the first member, that the lightest member, जो सबसे ऊपर जो member होता है, people are requesting ma'am Hindi, okay, all right. So जो सबसे ऊपर member होता है, the one that is the lightest, like boron, carbon, nitrogen, oxygen, fluorine. These ones, they differ. इनका जो reaction होता है, वो differ करता है, वो different होता है from the other. Why is it so? Why do they show an anomalous behavior? The reason is the first member differs because of two major reasons. The first is size. The first member is the smallest in size. Alright, because of this, the properties of the first member differs from those of the other members. The second important difference arises from the effect of d orbitals. So you will notice when we will talk about group 13 that the first member contains 2s2, 2p1. So it only contains the n is equal to 2 shell. But if you move down to aluminium, it will have 3s2, 3p1. This means that it has empty 3d orbitals. But in the case of boron and other lighter elements, d orbitals or empty d orbitals are not present. That means they cannot expand their covalency. That means they cannot form more than 4 bonds. So this is another important point of difference between the first member of each group and the remaining members. So first member cannot expand its covalency because of absence of d orbitals, and the rest of the members can. Now this is a very important point which has come up many a times in Neet. So this stems from the reasoning we just discussed because of absence of d orbitals. Read this. All right. बोरॉन की कोवेलेंसी ओनली 4 रह सकती है. वाई? बिकॉज बोरॉन में 2s और 2p है. ओके. अगर एक्साइटेड स्टेट देखिए बोरॉन की, 1 इलेक्ट्रॉन 2s में, 2 इलेक्ट्रॉन 2p में. अब एक और बॉन्ड फॉर्म करने के लिए ये एम्प्टी ऑर्बिटल है इधर. सो बोरॉन का क्या कोवेलेंसी हो सकता है? 4. That means boron can form Bf4 minus ion. But if we try to form Bf6 minus ion, what will happen? It cannot be formed. इसकी covalency cannot be 6. Why? Because there are no other empty orbitals in which any other electrons can be accommodated. Whereas in the case of aluminium, it can happen. So aluminium can form AlF6 3 minus. All right. Now the last point here concerns more with group 14, 15 and 16. So the lighter elements, carbon, nitrogen, oxygen, they can form, the lighter elements can form double or triple bonds, which are multiple bonds with each other. We will discuss this when we talk about group 15 and group 16, 14, 15 and 16. Alright, now we are going to start with group 13. So today's topic is group 13. All right. Group 13 elements. Group 13 elements are boron, aluminium, gallium, indium and thallium. So this table is from your NCERT. We will be discussing a few salient features of this table. Atomic number are 5, 13, 31, 49, 81, and these are the electronic configurations. So now you will see that for boron we have a full inner core of helium followed by 2s2 2p1. ठीक है? Aluminium में neon के बाद it follows by 3s2 3p1. ये valence electrons है, all right, 3s2 3p1. Gallium में 3d10 4s2 4p1. Do you see there is a difference? यहाँ पे 2s 2p 3s 3p, but here in the case of gallium before 4s and 4p there is a full 3d shell. It comprises of 10 electrons, right? In the case of indium you will see before 5s and 5p here there is a full complete 4d shell of 10 electrons, 4d10. And in the case of thallium you will see 6s2 6p1 is the valence shell configuration, but before that there is 4f14 5d10. This difference in the electronic configuration, the lot of properties of p block of group 13 elements differ because of this inner core of electrons. Here there is no 3d or no d electrons in both these cases, but here we have 3d 4d 4f and 5d, and all the other properties also we will discuss them one by one. Right. So we already discussed the outer electronic configuration. It is ns2 np1. So boron, aluminium, gallium, indium, thallium, 2s2 2p1 3s2 3p1 4s2 4p1, but gallium comes after the 3d series, so it has 3d 10 electrons also. All right, this is 5s2 5p1. Because it comes after the 4d elements, it has 4d 10 electrons before this valence shell, and here we have 6s2 6p1, and we have 5d10 and 4f 14 electrons also. So these are the electronic configurations of these elements. All right. Now you will see that what do you expect if you go down a group. एक group में ऊपर से नीचे जब आते हैं तो shells add on हो रहे हैं, electrons add on हो रहे हैं. This would mean that the atomic radii should increase, because boron से लेके thallium तक आने में lot of electrons are added. This means lot of shells are added, but that does not happen. It is expected to increase, but the atomic radius of gallium is less than that of aluminium. So the expected trend is boron, aluminium, gallium, indium, thallium. We are going down the group. So ये सबसे छोटा होना चाहिए और ये सब increase होने चाहिए. ये expected trend है. But इसमें एक exception कहाँ पे आती है, which is very important. You all should know this. Exception comes here. The atomic radius of aluminium is not less than gallium, it is more than that of gallium. So here the trend becomes gallium, indium and thallium. Why is it so? Why is it that gallium is smaller in size than aluminium? This again can be explained on the basis of electronic configuration. Going back, these are the electronic configurations. Here aluminium is 3s2 3p1, but when you talk about gallium, before the valence 4s2 4p1 configuration we have a full 3d subshell here, right? Now if you talk about the screening effect or the shielding effect, what happens, 3d electrons are very bad at shielding the nuclear charge, right? So whatever nuclear charge is there in gallium, it will not be shielded by the 3d electrons. They have a very poor screening effect or a poor shielding effect, and it will not be able to compensate for the high positive charge which is attracting the valence electrons towards itself. Now, if the positive charge from the nucleus is attracting these valence electrons more towards itself and the inner core electrons are not able to shield it, that would mean the size would contract or the size would become smaller. But in the case of aluminium, no such d electrons are present, and hence the size of gallium is less than that of aluminium. So this is the trend in atomic radii. Now ionization energy. Now ideally ionization energy again should decrease when you move down the group. Boron, aluminium, gallium, indium and thallium. So ideally size is increasing down the group. So if the size is increasing, it should become easier to take out one electron, but it does not happen. So from boron to aluminium a decrease takes place. That is normal. That according to the size is increasing, a decrease in ionization energy takes place. But there is a discontinuity between aluminium and gallium and between indium and thallium. So the expected trend is gallium, indium, thallium. Ideally it should just, wrong sign. This should have the largest. This is the expected trend. This does not happen. Again, there are exceptions here. Now, between aluminium and gallium, what happens? Ionization energy of aluminium is less than that of gallium, and between indium and thallium में ionization energy of indium is again less than that of thallium. This also stems from the difference in electronic configuration and the presence of d and f orbitals. D and f orbitals have a poor shielding effect. So whenever behind the valence electrons a full d or an f electron subshell is present, that would not screen the outer electrons from the nuclear charge well. If they are not screening the outer electrons, that means the total Z effective is very high on the valence electrons. This means that the size will contract. Hence, because of that, this anomaly is observed here, that the ionization energy of aluminium is found to be less than gallium and indium is found to be less than that of thallium. Next, electronegativity. Now, electronegativity down the group first decreases from boron to aluminium and then increases marginally. This also stems from the valence shell configuration and the presence of d and f electrons. Now, let's talk about the physical properties. Boron is a non-metal. It is a black solid and it has many allotropic forms. What is interesting about boron, that boron has an unusually high melting point. Now, why is it so? It is because of the structure of boron. Now, boron has a very unusual crystal structure. It has a very complex structure. And why is it so? It is because boron is electron deficient. We'll talk about electron deficiency of boron when you move on. So boron is electron deficient. When it forms bonds, it tries to remedy its electron deficiency by forming very complex structures, very complex allotropic structures, and it is very difficult to break the bonds between those complex structures, the force of interaction in that structure, which leads to the unusually high melting point of boron. Now, if you talk about gallium, there's another interesting thing that comes up. Now, gallium has an unusually low melting point. This is just 30 degrees. Why is it so? Gallium has a very low melting point because despite being a metal, despite being amphoteric, it is a metalloid, it does not form metallic bonds. Okay, it exists as discrete molecules. So instead of forming a metallic lattice, it forms discrete molecules which are held together by weak van der Waals forces. Because of that reason, it is very easy to overcome those forces and melt gallium, and hence it has a low melting point and it exists in liquid state during summer. Now it has a high boiling point, which makes it a useful material for measuring high temperatures. Now coming to the chemical properties, we will be talking about the oxidation state first. So we already know that the main oxidation state that is exhibited, that is the group oxidation state. The group oxidation state for group 13 elements is +3, which is a sum of the Ns and Np electrons. Now, due to the small size of boron, the sum of its first 3 ionization enthalpies is very high. This prevents it to form +3 ions and forces it to only form covalent compounds. But as we move from boron to aluminium, you will see that the sum of the first 3 ionization enthalpies considerably decreases, and therefore it is able to form Al3+ ions. This is a very interesting point. Boron only forms covalent compounds. Covalent compound would mean that it shares electrons and it does not form ions. Why is it so? Because of its small size and a high charge of +3. If we talk about Fajan's rule, if you think about that, if an ion is small in size and it has a high charge, this will favor covalency. Secondly, if the sum of 3 ionization energies, that means the total energy that is required to take out 3 electrons from boron for it to form an ion is very high, because of which boron does not form ionic compounds and it only forms covalent compounds. If you talk about compounds of aluminium and other elements like AlCl3, so these compounds are also covalent in the anhydrous state. But in an aqueous solution, what happens? The energy of hydration, the energy released when this compound is hydrated in water exceeds the ionization energy. So a lot of energy is released, and which is more than the ionization energy that is required for AlCl3 to break down into ions. That is the reason that rest of the compounds apart from boron, they form ions in solution. Primarily, otherwise they are covalent in nature. Alright. Now we'll come to the inert pair effect that we spoke about. So group oxidation state is +3, right? But as you move down the group, what happens? That the stability of an oxidation state that is 2 less than the group oxidation state, that means +1, progressively increases, right? So thallium here almost exclusively shows +1 state and forms only a very few compounds in the +3 oxidation state. Why does that happen? So this happens because if we talk about the electronic valence shell electronic configuration, it is Ns2Np1. For these elements to show a +3 state, these electrons here in the Ns orbital need to be unpaired and be promoted to the Np orbital, right? So now there are 3 unpaired electrons and a +3 oxidation state will be observed. What happens when you move down the group? The Ns2, the 2 electrons in the s orbital stay paired. They stay paired. They do not get unpaired. When these two stay paired, 2 electrons are staying paired, only 1 electron is available in the p orbital for bonding. That means a +1 oxidation state will happen. So the inability of these s electrons to participate in bonding is called the inert pair effect. Now thallium shows +1 oxidation state and the stability of this oxidation state increases as you move down the group. but this is not the reason. The inert pair effect is only telling you what is happening. It is telling you that the S electrons are not participating in bonding, but the reason behind it is energy. The reason behind inert pair effect is energy. So the energy that is required to unpair these two electrons is not compensated by the energy that is released when a compound is formed. So the molecule would not want to be formed. And this is again because of the presence of D and F electrons. So D and F electrons have a very poor shielding effect. Now the effective nuclear charge is very high on these S electrons. Because of the pull from the nucleus, these two S electrons do not want to get unpaired because of the high Z effective, which happens because of the presence of D and F electrons. So this is the reason behind inert pair effect. So basically it does not tell you why it is happening, it is only telling you that a +1 state is more stable. The reason behind it is energy, and that is because the Z effective is so high that it is holding on to the S electrons and not letting them be unpaired. Right. So this is the inert pair effect. Now another very interesting thing in the chemical properties of group 13 is boron. So boron in its trivalent state, for example in BF3, it behaves as a Lewis acid. This is what we were talking about. Now why does boron in its trivalent state like in BF3 behave as a Lewis acid? What is a Lewis acid? A Lewis acid is an electron deficient species. An electron deficient species is something that would want to take some electrons, and BF3 is a Lewis acid. Why is it so? If you look at the electronic configuration of boron, it is 1s2, 2s2, 2p1, right? If you see the valence shell configuration, it is this. In the excited state, the electrons become unpaired, and this is what you get. So this is 2s, this is 2p. Now if it is forming bonds with 3 fluorines, fluorine, fluorine, fluorine here, they are forming bonds together. So what is the total valence shell count here? So we have 3 from here, 3 from fluorine, so we have 6 electrons in total. That means BF3 molecule does not have a noble gas configuration. It is 2 electrons short of the nearest noble gas configuration. That is the reason it is termed as an electron deficient species. So this is the reason in the trivalent state BF3, and in fact AlCl3 also, all the group 13 elements, they act as Lewis acids. Now if you read this line here, it is stemming from the anomalous behavior that we discussed. So because BF3, ALF3, AlCl3, all these are electron deficient compounds, right? They would want to gain a pair of electrons and attain a noble gas configuration because that will increase their stability. So in water, BF3 or trivalent boron hydrolyzes as BOH4 minus. Okay, it now acquires 4 OH hydroxyl ions around it because 2s and 2p in boron gives us 4 orbitals. That means 4 bonds can be formed with boron, right? But boron cannot exceed its covalency beyond 4. Whereas in the case of other trichlorides like AlCl3, what happens? We get this ion AlH2O6. How does this happen? So if we talk about aluminium, atomic number is 13. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. So if you talk about the valence share, 3p1. in the excited state, this is aluminium. When it forms an aluminium ion, these orbitals are empty now. How is it having a covalency of 6? It has 6 water molecules. This bracket needs to come here. It has 6 water molecules associated with it. What is happening? 4 orbitals are from here, 3s and 3p. Now, because the third shell is there, it means that there is an empty 3d shell also present here. So, we have empty 3d orbitals. Now, this means that aluminium can expand its covalency. It is not restricted to just these orbitals like in the case of boron, because this was n equal to 2. In the case of n is equal to 3, we have empty 3d orbitals also. So, water molecules can form bonds here and here. So, do you see the 6 water molecules that can now donate their lone pair from the oxygen to these empty orbitals and form this octahedral complex. This means the hybridization of aluminium here would be sp3d2. sp3d2. So, this is the difference between boron and the rest of the elements. Boron can only form a tetrahedral complex in water, whereas the rest of the elements like AlCl3 aluminium can form an octahedral complex because it can expand its covalency to 6 rather than staying just at 4. And the hybridization would be sp3d2 because it is using the 2 3d orbitals also from here. So, these hybridize together to give sp3d2. Right. Now, we have discussed the basic chemical reactivity. Now, we have to be very specific and talk about reactivity towards air. When we talk about the first one is reactivity towards air, it means we are talking about reaction with oxygen and nitrogen here now. So, crystalline boron does not react with oxygen or nitrogen, but amorphous boron reacts with oxygen and nitrogen at high temperatures, so it forms boric oxide. So, boron reacting with oxygen gives us B2O3 and boron reacting with nitrogen gives us boron nitride at high temperatures. Also, aluminium reacts in the same way. Aluminium also reacts with oxygen to give us Al2O3 and it reacts with nitrogen according to this reaction here to give us aluminium nitride. Now, what is interesting is that Al2O3, the reaction of aluminium with oxygen is highly exothermic and it is almost explosive. A large amount of heat is produced. So, this was used in bombs in World War II. So, there is a thing called thermite mixture, which is aluminium with Fe2O3. Fe2O3 provides the oxygen for this reaction. So, aluminium reacting with oxygen giving us Al2O3 is called the thermite reaction. The rest of the elements also react with oxygen giving us these oxides, and indium and thallium do not react with nitrogen. All the elements react with oxygen, just indium and thallium do not react with nitrogen, rest of them react with nitrogen to give En, where E is the element from the group 13. Alright, another interesting thing which we have already discussed is the oxides, nature of oxides. So, boron trioxide is acidic in nature, aluminium and gallium oxides are amphoteric, and those of indium and thallium are basic in their nature. So, an acidic oxide would react with a base to give us salt and water. A basic oxide would react with an acid to give us some salt and water. An amphoteric oxide would mean that it reacts with both acids and bases. Okay. Next reaction is reactivity towards acids and alkalis. Now, boron does not react with acids and alkalis, but aluminium does. So aluminium is amphoteric in nature. It is a metalloid. It reacts with both acids as well as bases. So look at this reaction here. Aluminium reacts with dilute HCl to give us AlCl3. Since it's an aqueous solution, we get ions Al3 plus and Cl minus, and hydrogen gas is released here. So on a reaction of aluminium with an aqueous dilute acid, we get hydrogen gas. Aluminium also reacts with a base like aqueous NaOH, this reaction here, and forms aluminates. So aluminium reacting with NaOH in an aqueous solution give us NaAlOH4. So this is sodium tetrahydroxoaluminate, and hydrogen gas is again released. So you need to remember that when aluminium is reacting with HCl or NaOH, in both the cases hydrogen gas is released. Similarly, gallium is also amphoteric. Gallium will also react with acid as well as base. Indium and thallium do not react with bases. Alright. Another interesting thing which has come up in the paper also is why is aluminium rendered inactive by nitric oxide? That is because nitric oxide is a good oxidizing agent. So what happens, it forms a thin film of oxide on top of aluminium of Al2O3. A thin film of aluminium oxide is formed on the aluminium metal, because of which the further metal is protected, and hence the reaction does not take place. Hence it is rendered inactive in the presence of nitric oxide. The third is reactivity towards halogens. So all these elements react with all the halogens. So fluorine, chlorine, bromine, iodine. All the group 13 elements react with halogens to form trihalides. So we'll have BF3, BCl3, BBr3, Bi3. Similarly for aluminium, for gallium, for indium and for thallium. One exception arises here also, which has again and again come in the paper, that is with thallium. So for this you need to go back to the inert pair effect. What happens in the inert pair effect? You see, as you move down the group, the +1 state becomes more stable, right? So thallium forms trihalides with chlorine, with fluorine and with bromine, but does not form trihalides with iodine. Thallium with iodine forms thallus iodide. This, when further reacting with iodine, gives us this compound TlI3, but this is a very unusual compound. In thallic iodide, here it is not thallic iodide, thallium is existing in its +1 state only, because I3 is present as I3 minus ion, triiodide ion. So thallium does not form TlI3, it forms Tl plus I3 minus, in which thallium is in its +1 state, because +1 oxidation state is the most stable for the element which is at the bottom of the group. So inert pair effect also comes into play here. Now this question here is from your NCERT. White fumes appear around the bottle of anhydrous aluminium chloride. Now what happens if anhydrous aluminium chloride is kept in a bottle? It partly hydrolyzes with water, which is present in the atmosphere, and it gives HCl. Now HCl, when moist, appears white in color. So those are the white fumes that appear around the bottle. This is it about reactivity towards halogens. Right. Any doubt? Non-metallic bond. It is metallic bonds are not a part of p block elements, so it is not a part of your syllabus right now. So you just need to know that metals form metallic bonds with each other, in which the valence electrons is not shared or given to the other atom. It just roams around freely in the crystal lattice. All right. Okay. This topic is a repetition of whatever we have done till now. It is given separately in your book, so we are just doing it. We've already talked about the anomalous behavior of boron. It cannot expand its covalency, so it only forms MO4 minus, whereas rest can form an octahedral complex. Now, boron trifluoride is a Lewis base. It reacts with Lewis bases because it is a Lewis acid. It is an electron deficient compound. So, if it's reacting with ammonia, which is a Lewis base because it has a lone pair, ammonia can donate its lone pair into the empty pz orbital, and we can get this adduct here. Right. Now, boron is unable to form BF6 3 minus, which we have again talked about it. This is due to the absence of d orbitals in boron. So, rest of the elements can form octahedral complexes. They can expand their covalency to 6, but boron cannot do so, and hence it does not form BF6 3 minus ions. Moving on, we don't have a lot of time left. I'll quickly go through these, some important compounds of boron. These are very important. So, you're talking about 3 compounds. One is borax, one is orthoboric acid, and the third one is diborane. Let's go through these quickly. Borax, it is the most important metaborate, and the formula is this one here. So, what happens in borax? The structure of borax is like this. Look here, what's happening to boron. So, we have BOB bonds, and every boron has an OH attached to it. So, this is the ion that is present in borax. So, we have planar triangle structure here. This is boron, OHOO. So, this boron is attached to 3 oxygens, sp2 hybridized, planar triangular structure. Here also 3 oxygens, sp2 hybridized, planar triangular structure, and these 2 borons are tetrahedrally bonded. So, they are bonded to 4 oxygens. So, this is the unit here that is present as an ion. So, the correct structure sometimes is written like this. But for our purposes, we usually write Na2B4O7. It is easier to write the reactions. Now, the important reactions are borax gives an alkaline solution in water. So, what happens when borax is dissolved in water? It gives us NaOH and orthoboric acid. Orthoboric acid is a weak acid, and NaOH is a strong base, so the solution is alkaline. Next is a very important test that is called the borax bead test. Borax bead test. Now, a very interesting property of borax is that when you heat borax, first it will lose these 10 water molecules which are associated with it, and on further heating it will form a sodium metaborate, which is a glass-like structure, and it becomes a bead. It becomes a bead-like structure on further heating. So, this on heating loses water molecules, and on further heating forms NaBO2, which is sodium metaborate. NaBO2 is sodium metaborate, and boric anhydride B2O3. Now, what is interesting is the metaborates of some metals are colored. So, if you have a metal oxide and you heat it with borax on a platinum wire over a flame, a Bunsen burner flame, a colored bead will be obtained, because here, if let us say you have cobalt oxide and heating with borax, it will give us a colored bead of cobalt metaborate now. So, COBO2 whole twice. So, this is a blue colored bead. So, this test can be used for identification. So, it is used for identification of those metals which give colored metaborates. So, this reaction is so useful that because of this simple reaction, it was the first time that it was proven that vitamin B12 has cobalt in it. So, it was proven through this interesting reaction. Yes, this is somebody is asking me, is this relevant, Aman? Yes, Aman, this is extremely relevant because all these reactions have come up again and again. You need to know the borax bead test, and you need to know why is it that Borax prepares in water, it gives an alkaline solution. These reactions are very, very important. We'll have to end our class here. The other remaining compounds are orthoboric acid and diborane. We'll try to give you some PDFs regarding these so that you're able to prepare. Thank you so much. I'll see you in 15 minutes. So we have a selection hour coming up where I will be taking up questions from this topic here, and we'll do some previous year questions also. So it is very interesting. I hope to see you around, I'll see you at 5 then. Thank you.